Hi everyone. We're going to look at operations with power series. So Maclaurin and Taylor for the most part, but this would apply for any power series. So I'm going to start with just basic derivatives and integrals, and it sounds like that shouldn't be the most basic operation, but with power series it actually does end up being sort of the simplest ones. So specifically, if I think about the concept of a Taylor series. So for some function which is defined according to a Taylor series, which we can recall is this, k equals 0 to infinity of some coefficient, whatever that ends up being. Sorry, this is just generic power series, not the Taylor series specifically. X minus a to the power of k. So that's how our function is defined. Then we get just it's a power. And it's a power of a binomial that has a derivative of 1. So the derivative of this function is simply going to be the sum of all these terms from k equals 0 to infinity of whatever the coefficient was to begin with, times k times x minus a to the power of k minus 1. So that's simply the power rule for the derivative. And going the other way around, we've got the integral of f of x dx is going to basically be the sum from k equals 0 to infinity of some coefficient divided by k plus 1 times x minus a to the power of k plus 1. Now note that this will not contain a constant term, so we need some sort of constant because this is an integral. So just like any other indefinite integral. So let's look at a specific example. We're going to look at a specific example that is a pretty easy one where we know what the derivative and integral already are. So we're going to look specifically at the Maclaurin series for e to the power of x. So we're going to look at f of x equals e to the power of x, which, if we will recall, goes something like this. So starting at k equals 0 up to infinity, our coefficients are just 1 over k factorial here. And because it is a Maclaurin series, it's centered at 0, so we just have this. So to remember what that looks like in expansion, because that will help us when we're thinking about the derivative and the integral. This is 1 plus x squared over 2 plus x cubed over 6 plus x to the power 4 over 24, and so on. Now, if I look at what the derivative of this is going to be, and I'm going to actually work with it in its expanded form, because there I see it a little more clearly. So I have f prime of x. Well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 is just going to be x. X cubed over 6 is going to become 3x squared over 6, which is x squared over 2. X to the power of 4 over 24 is going to be 4x cubed over 24, which is x cubed over 6, and so on down the line. So we see that in each case, because our denominator is k factorial, we're going to end up with k times x to the power of k minus 1 over k factorial, which is simply the same thing as x to the power of k minus 1 over k minus 1 factorial. This case, though, our k's are starting at 1, basically, because we're needing to get back to that constant term at the start so that we would have a k minus 0, or k minus 1, so 1 minus 1. Essentially, looking at all of this, that is e to the power of x. So we can see exactly what we expected to see. There should be no surprise here that the derivative of e to the power of x is e to the power of x. So we see that showing up in that Taylor or Maclaurin series. The same thing would happen if I was going the other way around. If I'm wanting to do the integral of f of x dx. So in this case, well, I'm going to put my constant at the front because that's where the constant is in these polynomials. We're starting from the 0 power and then going up towards an infinite power. The antiderivative of of 1 is x. The antiderivative of x squared over 2, well, that's going to be x cubed, and then I'm going to divide by 3, multiply that by the 2, and I get a 6. Antiderivative of x cubed over 6, well, that becomes x to the power 4 over 4 times the 6 that's already there, which is 24, and so on and so forth. So we can see that in this case, what we're getting each time is x to the power of k plus 1 over k plus 1 times the k factorial that was already there. Well, k plus 1 times k factorial just means that I have a denominator of k plus 1 factorial. So this is x to the power of k plus 1 over k plus 1 factorial. So in this case, I still end up with the exact same thing, except instead of starting at the 1, I'm starting at x. Well, here's the thing. E to the power of x has that 1 in it. But this constant could be anything. It's arbitrary. So I'm going to call that C1 plus 1, so that I can now write this as some constant, a different constant than the one I initially started out with, plus 1 plus x plus, oops, I missed my x squared over 2 in here. I'm just going to squeeze it in here. That was the antiderivative of x. Plus x squared over 2 plus x cubed over 6, etc. Or in other words, exactly what we expected to see. We've got our e to the power of x showing up here. So the integral of f of x, which in this case was e to the power of x, dx, is just e to the power of x plus some arbitrary constant. Now, in a lot of ways, doing calculus with power series is way, way, way easier than trying to do calculus with some of these other functions, especially when we're integrating, because when we're using a power series, we're just integrating a polynomial, as opposed to cases where we have something that maybe isn't quite so straightforward to integrate. Now, we are not going to belabor the point of integrals and differentiation, because they're quite a bit simpler to do, because they are just polynomials. So any kind of Taylor polynomial or Maclaurin polynomial, you can derive and integrate using just power rules. You do sometimes have to be careful about what that constant is representing. So I usually will use a subscript to represent different constants. Now, we can do other types of operations as well. So let's say, for example, I want to consider a function where I have f of x equals sine x plus cos x. Now, if I want a Maclaurin series for this, so find a Maclaurin series, I can just go from the definition of a Maclaurin series, and I can derive this function, first derivative, second derivative, and so on, and go on from there. But given that this function is created from two other functions whose Maclaurin series I know that the sine of x is equal to x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial, etc. And I know that the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial, etc. Then I can actually just add these two together and figure out what the new one would have to be. So it does save me. It's not like this one would be a really hard one to figure out from the actual definition of Maclaurin series, and you would be completely welcome to do that. But the sum of these is f of x. So I get 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial, and so on. So that gives me a general idea. Now, the pattern is not as straightforward as a simple alternating series, so it's a little harder to express with an expression. not really important because usually the thing that we're doing with this, we're using it to estimate values. And when you're using it to estimate values, the first, well, in this case, I've got 6 terms. The first 6 terms is going to be usually plenty to get the precision that you need. Now, that's a little more complicated. So addition, adding 2 Maclaurin series together, totally can do that. It gets a little uglier if what I'm trying to do is multiply. So let's consider a new function, g of x equals e to the power of x sine of x. Now again, feel free to find your Maclaurin series from the definition. So just by going through first derivative, second derivative, so on, hoping to find a pattern. But again, in this instance, I do have 2 known Maclaurin series. So I know that e to the power of x is equal to 1 plus x squared over 2 plus x cubed, over 2 factorial. It is just over 2, but I'm going to write the factorial for consistency. So this is my e to the power of x series. And that goes on and on and on forever. And my sine x, as we just saw above, x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial, etc. Now, this is a fair bit more complicated because multiplying 2 polynomials involves distributing every term with every other term. And in this case, we have infinite polynomials. So that's, well, I don't know about you, but I don't feel like distributing infinite terms with infinite terms. That seems like it might take a ridiculous amount of time. But if I can figure out, well, what terms are going to be my power of 0 terms, my power of 1 terms, my power of 2 terms, and go from there and try and find a pattern. So, for example, I am not going to have a constant here because sine x doesn't have a constant. So in order to get a constant term, I would have to be multiplying a constant by a constant. That's never going to happen. So now I think of, okay, my degree 1 term. My degree 1 term can only come from this multiplication, 1 times x. So if I multiply these two together, I'm getting g of x. It's going to have a linear term of x. Now I'm going to think about my quadratic term. My quadratic term comes from x times x. It could come from a quadratic times a constant, but while e to the power of x has a quadratic, sine x doesn't have a constant. And while e to the power of x has a constant, sine x doesn't have a quadratic. So there's no other way here that I could get a quadratic term. So my only quadratic term is coming from x times x. Okay, so that means I have a quadratic term of x squared. It does start to get a little more complicated. So I'm going to try and find some more colors here so that I can represent these. So let's go with orange. So I'm going to use orange for the cubic term. The cubic term comes from 1. Why did that not switch to orange? That's unfortunate. Let's try that again. Orange. The constant times the cubic, or the quadratic times the linear. So those are the 2 places a cubic term is going to come from. Have a quick look. It could come from the constant x in e to the power of x times a quadratic in sine x, but there isn't one. It could come from the cube in e to the power of x being multiplied by a constant in sine x, but there isn't one. So these are the only 2 places that a cubic term can come from. So my cubic term comes from 1 times negative x cubed over 3 factorial. So that's going to be negative x cubed over 3 factorial. And it comes from x squared over 2 factorial times x. So that's x cubed over 2 factorial. Then my degree 4 term, we're going to go as high as the degree 5 term and then try and figure out a pattern from there. So my degree 4 term, as I get further up, they are going to get a little more complicated. So I'm going to use purple for this one. My degree 4 term. All right, degree 4 term is going to come from x times x cubed over 3 factorial. And it is going to come from x cubed over 3 factorial times x on the other side. degree 4 term. Okay, so I'm going to write those down. So I've got minus x to the power 4 over 3 factorial plus x to the power of 4 over 3 factorial. Again, make sure that you've got all of them. So think through. I could have a quadratic times a quadratic, but sine doesn't have a quadratic in it. I could have a degree 4 times a constant, but sine doesn't have a degree 4. And while e to the x has a degree 4, sine doesn't have a constant. So I'm not going to get any others. So the handy thing about these ones, they actually disappear. And my degree 5. All right, so I will use, let's say, pink for my degree 5. So my degree 5, well, that comes from my constant times the degree 5. So that one is going to give me, might as well keep it in pink. Okay, so that one is going to give me positive x to the power of 5 over 5 factorial. A degree 5 can come, so I have a constant by a degree 5. I can have a linear by a degree 4, but the linear in e to the power of x can't multiply with a degree 4 in sine. So the linear in sine multiplied by the degree 4 in e to the power of x. So that's going to give me e to the power of 5 over 4 factorial, or x to the power of 5, sorry, over 4 factorial. It can come from a degree 3 times a degree 2. So I have a quadratic term and a cubic term here. So that's going to give me negative x to the power of 5 over 2 factorial, 3 factorial. The cube in e to the power of x doesn't have a quadratic in sine x to multiply by. I already multiplied. Okay, so those are the 3 terms that are going to make this up. Now this carries on for quite some time, but we're not going to worry about it. We're just going to get up to the degree 5 term. So simplifying this out, now I need common denominators in order to add these fractions together. So in the first case, I'm going to call that negative x cubed over 3 factorial plus 3x cubed over 3 factorial. So this now gives me, well, I've got my, oops, I'm going to switch to blue. I've got my x plus x squared. I now have 2x cubed over 3 factorial. Yep. Then I've got, in this next case, so I don't have a degree 4 term, so that's nice. If I look at the degree 5, okay, so I'm actually going to look at these as numbers. 6 times 2, yeah, okay. So this is 120 as a denominator, this is 24, and this one is 12. So my common denominator is going to be 120. So I've got x to the power of 5 over 120 plus 5x to the power of 5 over 120 minus 10x to the power of 5 over 120. So that is going to end up being negative 4x to the power of 5 over 120. And this would go on for a while, but 4 terms is usually enough if I were using this to estimate values. And if it were a question I were asking you, I would tell you, find the first 4 terms or find the first 5 terms, and I would always specify non-zero. So find the first 4 non-zero terms, because this goes up to the 5th power, but of course I have 0 terms in there. There's a 0 constant term and a 0 x to the power of 4. So what we get when we simplify this, 2 over 6, so I get x cubed over just 3, minus x to the power of 5 over 30. And that goes on and on. So those are the first 4 non-zero terms of this expansion. I don't see a pattern yet. That's okay. If it takes more than 4 or 5 terms, I'm not looking for the pattern from you. I'll just be specifying a set number of terms to be looking for. So that's really all we're after here. So for operations, it's fairly straightforward if we're dealing with just derivatives and integrals because they're polynomials. Even if they're not centered at 0, they're still binomial powers that have a derivative of 1. So the derivative and the integral are just using power rule. If I'm adding or subtracting two known Maclaurin series or Taylor series, again, fairly straightforward because I can just match up what's happening with the like terms. Quite a bit more complicated if we're dealing with multiplication. In those cases, we would specify to you a certain number of terms to be looking for. And division, we're not even going to touch. That's too nightmarish. At that point, you would just be better off starting from scratch and figuring out your Maclaurin or Taylor series from the definition. Now, you can find practice for these in your online, the calculus option textbook. And this is section 3.3. Operations with power series.